People online, are you able to hear me?
Yes, sir. Good morning, sir. Good
Very
morning, all
good
of you.
morning. Thank you. Thank you. Been told let's wait for a few more minutes. I apologize. So I'm going to wait until what time is it now? 9:25 to start. 3 minutes more. While we wait, I'm happy to entertain questions or comments. No questions, no comments?
Sir, I have a question, sir.
Okay, was it Chandrika Khan?
Yeah, sir. My question is related to ABS, sir. Anti-lock braking system, sir.
Okay.
So what kind of, actually in India in 2019, it was mandatory to implement the ABS system in two-wheelers.
Okay.
Earlier it was more than 150 cc engines. Now it has come to 110 cc like that.
Okay.
So what kind of the collision, sir? It prevents basically in those vehicles. Means below 150 cc, those who are implementing, because there is no such kind of more studies in Indian context. So what kind of collision like other continent actually it is preventing? So I would like to know some.
Thank you, Chandrika Verma. It's a good question. I don't have an answer. That's not something that I have studied. And in the United States, as I mentioned earlier over the last several days, motorized two-wheelers or even bicycle usage accounts for a very, very, very small proportion of travel, less than 3% in total, maybe 2%. And I'm not aware of any studies that have been done about this. I know for four-wheelers and more, I can tell you things, but for two-wheelers, I'm sorry, I don't. One source that you could go look for is the Transportation Research Board. So the T for transportation, R for research, B for board, trb.org. If you want to find any reference that is related to transportation, that is perhaps the best source to go. Go to trb.org, and then within trb.org you will see at the top there is several items on a banner, links. Click on the link that says I think resources and databases, or databases and resources, something of that sort, and within that select TRID, Transportation Research Information Database. What was that, Shwinton?
So actually, regarding this, I think I have a little bit of answer to his question. Sir, basically ABS is anti-locking braking system. So in the non-ABS system or IBS system, if we apply the brake, it will lock the both of the wheel or the front wheel of the bike. So there is more approach to the skidding of the bike. If we apply the brake with more pressure, it will lock the wheel and it will skid the bike. And in ABS, what is it will do? It will just like this is the wheel. If you consider this as wheel, and this is the braking what is the braking pad. It will just not locking it. It will just applying like this.
Yes.
If you can see it in my hand. So it will just slow down the vehicle in lesser time, and it will prevent the skidding. So
yes,
this is the main concept of ABS.
Excellent, Das. And so that is, you're describing the mechanics. So I think what Chandrika Verma wanted to know was, have there been studies that looked at how effective it is, how safe it is, or what are unintended consequences? So I don't have references. So please look at the trb.org and go to TRID, TRID, and if you they give you a lot of options to search, and you will find any relevant reference. You can search by keyword, you can lock it down to a geographic area, India or a continent, so on, or type the keywords. Many of them you will be at least able to see the abstract and who the authors are. Some of these articles, if they are copyrighted by a journal, for example Elsevier Press or Taylor and Francis, unless your organization subscribes to that, you may not be able to get access to that manuscript. So I'm sorry I don't have more details for you.
Thank you, sir, for yeah. Thank you, sir. Thank you.
Yeah. The other thing that what Shanthan Das also said is it prevents the skidding, but what happens in two-wheelers is if you apply the brakes to the front wheel and you just jam your brakes without the anti-lock brake, you could have what is called a cartwheeling effect. The back wheel is still carrying the momentum and moving, and so you could flip over. All right, any other questions, comments? So in the next approximately 70 minutes, 75 minutes, up to 10:45 is what I am aiming for. I wanted to give you some examples to tie together a lot of the concepts that we have seen, and specifically the first few slides are just traditional crash data analysis, but subsequently I'll show you the use of emerging tools and technologies, data sources. But before that, I want you to think about this following question. I will come to you with this question later on. It is an individual exercise, not a team exercise. So I will call on anybody and you have to be ready to answer. It will be after 1 hour, it's not going to be here, after the chai break. Those of you who are here, chai break. Those of you who are not here, sorry once again, I don't have the technology to just beam it out to you from here to there. Okay. So the question is, identify where on planet Earth you have lived the longest that you can remember. So maybe after 5 years of age. Town, city, village, district. So think about where you have spent the most time in your life. In that area, from your experiences, I want you to base your experiences, your observations, what people may have told you, what you have seen, not what you have done in research. What are 3 most challenging or serious road safety issues that come to your mind? So we will start the tutorial session with this, and I will call on everybody. What are the 3 most most critical road safety issues in the place where you have lived the longest that you can remember? So, and I usually tell before 5 years of age, memory is not as good, but after that, maybe when you started going to first grade, first standard or so. And I'll tie that to a few other things that we've been doing in the class, or I'll make you tie it to that. Is that a deal? Does anybody have an objection to this?
No, sir.
Okay. I want you to own this. All right, so I'm just going to, here are the standard objectives. Many of these are building on what we have seen, but the big part is what I have in number 5 and number 6, applying it to real world situations, the theory that we have seen, and how do we use that. I realize almost everything that I'm going to show is from the United States and from where I live for the most part, the metro area of Las Vegas, but there are some others. I think I have one thing from Dubai. You need to think about how that might be applicable to India. So the implementation case studies, I started with this yesterday. One simple thing, I don't have any graphics on this, has to do with urban intersection, safety at an urban intersection. We are trying to link data from traffic signals, video analytics, crash data, what we have seen, and traffic volumes. The video analytics, I will show it to you later after about 10 minutes or 15 minutes, some examples. But here I'm just telling you how we put these together. And the specific metric we looked at is time to collision. If you had 2 conflicting trajectories, if the 2 had continued along their paths without a change in speed or in their speed profile, some of them may have been accelerating or even decelerating, how much time might have elapsed before an actual collision would have occurred? And then they take some abrupt maneuvers, such as we talked about. Normal braking is about 0.3 G, maybe 0.4 G under emergency, 0.5 G under emergency, if they go to much greater than that. So that's the time to collision. So these are great indicators of not crashes, but the potential crashes. So if you see that same thing over and over and over again at one particular location, what that means is there are some issues either related to the posted speed limit, maybe to the sight lines or sight distances, or maybe to the traffic signal timing, or maybe to the signage leading up to that particular location. So what it resulted in was retiming the traffic signal to reduce conflicts, including maybe having protected left turn for us, protected right turn instead of right turn on permissive. So this is an example that was done in Toronto under the MOVE project, and they did this at 22 intersections, signalized intersections, and they report that they reduced conflicts by 17%. That's substantial. Ritvik, did you have a question? No. So the next one was a corridor, not a specific location. In the United States, we have a lot more adverse weather for about at least 50% of the geographic area of the United States, where in the winter we have ice and snow, and in some other areas we have very dense fog. Rain is there, but it's not as big a hazard for the most part. So tying weather data from sensors, and I'll talk to you about where the sensors are, relating that to the pavement condition, basically the friction that you are able to generate, the braking forces that you will be able to generate based upon the pavement conditions, monitoring the speeds of vehicles, and looking at historical information on crash. When we had these kinds of conditions, it ended up in such and such crashes. So now when we monitor real time, can we provide feedback or roadside information, variable message signs, so on. So the theoretical approach was a base, empirical base, so if this then that type. And so the outcomes were variable speed limits. So you can change the speed limit at any one location if you have an electronic board. It's not a painted sign. Electronic board you can control remotely. How do you get the weather data and pavement condition data? So there are lots of companies who do this. One example, is there anybody who has not heard about the Michelin tire company? Michelin tire. Is there anybody who has not heard? Raise your hands. Okay. Left hand, the other left hand. Daniel, you have heard of Michelin. Good. Online, if you have not heard about Michelin, please raise your hand. Tushar, okay. So they are one of, I shouldn't say the largest, one of the large tire manufacturing companies, and many of their tires usually are on higher end motor vehicles. But nowadays they've made it into even medium cost vehicles. So they've been in this business for many years in terms of selling tires. But over the last decade or more, they've also started getting data from their tires. I work with Michelin Tire Company on some research initiatives, trying to collaborate with them. We still don't have that. I don't have any personal shares or stock in Michelin, so I'm not trying to promote them. So they get location, time, then speed, acceleration, things that we talked about. But because they have technologies that will measure the traction that the tire has with the pavement, they can figure out whether it's the skidding or not as much friction being generated. So when, where, what, and they can tie it to environmental conditions there. So now you got tying weather and road surface conditions. Other weather data in the United States, the state PWD, Public Work Department, or the Department of Transportation, particularly where we have very harsh winter conditions, they have sensors all over. When I say all over, probably every 3 mile, 5 mile, 10 mile, depends upon it. If it is hilly terrain, they may have it more closely spaced. And that measures not just temperature, wind speed, humidity, pavement temperature. They have sensors embedded in the pavement that measures, because the air temperature could be quite different from the pavement temperature. And combined with precipitation, rain or snow, you could have some very hazardous conditions. They detect that and use radios. For example, in the US, it is fairly common to still have AM radios for road weather information or road traffic condition information, broadcast it over that. But we can also do variable message signs. And nowadays, many agencies have smart apps. If you download their app, you can get travel conditions, travel speeds, traffic volumes, construction zones, so on and so forth. So they can use that to push information and geofence. They don't have to push it to everybody, only people who might be affected in that area. So you can be selective, because if you keep broadcasting messages that are irrelevant, the users will soon start saying, that's one more boring message. Whereas if it is something that pertains to them, oh, I need to pay attention. So that's another example. So now I'll go to a very traditional project. This is something that we are working on right now in Las Vegas. And there we have in the US over the last 5+ years, bless you. We say bless you when somebody sneezes. Okay. In my village we say something else, yeah. So complete streets. The concept of complete streets is to plan, design, construct and operate roadways that serve all road users. Over the last 60-70 years, from the 1950s, late 50s on until about a decade ago, much of the emphasis has been on motorized vehicles, 4-wheel vehicles or more, buses, trucks. So the vulnerable road users such as pedestrians, bicyclists, those who may have mobility impairments. Well, let me make sure I turn off my phone. Thank you. Mobility impairments may not have as good an opportunity to move on these roads. What are examples? Don't have proper sidewalks or footpaths, as we call them here. Or you have a footpath that is maybe 1.5 meters wide, that will very good to move a wheelchair. But because you have this electric pole or telephone pole right in the middle, all of a sudden it becomes impassable for the wheelchair person, right? That's a very simple example. Or when you have footpath to road, they have to cross. You don't have a curb that the wheelchair bound person can get from the footpath onto the road, or the gradient of the transition from the footpath to the street is too steep. So that's the concept of complete streets, is plan, design, construct and operate streets for all users. So in this particular, so this is a map of some areas around Las Vegas. Just to give you a sense, here's the main airport for Las Vegas and here's the university where I work is here, UNLV, and here is where you might have seen photos or videos of what is called the Las Vegas Strip, the corridor where we have huge hotels, entertainment facilities, so on. So here are some major, Las Vegas has a very nice rectangular grid network where the major streets, the major arterials, remember I talked to you about the functional class, are 1 mile apart. That has to do with going back more than 150 years to the survey. Survey said those were section lines, if you know surveying terminology. So that's every 1 mile here. So we have a major arterial every mile. And these are the roads on which our public transport, the bus network operates. There are some that operate on the minor streets, but the subarterial, half mile, but most are on this 1 mile. So what we are doing is comparing several road corridors to transform them from what they are now to what might be a complete street. But they don't have the money to develop all of them. So they wanted us to come up with a methodology to compare what the benefits are of. Like you asked me yesterday, Ritvik, how do you use the benefit cost and the VSL? So one of the things, angles we are looking at is safety. The others I'm working with colleagues in economics and land development to look at how much retail space is there, how much residential space, what is the density, is it a high-rise residential versus single home, the villa type, because each of those has different tendencies to generate pedestrian and bicycle trips. The roads are already designed for the cars, trucks and buses, but what we want to do is improve them to better serve the vulnerable road users. So we looked at several things, is these corridors, and put what you see here are buffers. I'll show you more details in the next one. Next slide. and we designed a half a mile buffer and 1 mile buffer. This is the maximum extent that somebody is likely going to. If you have bus routes on two major arterials that are 1 mile apart, on average a person is only going to walk half mile, right? So we are trying to figure out how many people are within the walking distance of these corridors. Then we looked at the location of bus stops. I showed you an example 2 days ago, 3 days ago at each intersection. Where are the bus stops located? Where is the farthest bus stop? And then for each bus stop, we know how many people are getting on the bus, how many people are getting off the bus. So that gives us a measure for activity exposure. People who are getting on and off the bus are walking. Some of them may have to cross the street, some of them may not have to cross the street, but all of them need to use the footpath, sidewalk. So that's trying to get an indication of the measure of demand. So that's one metric. The other metric we are looking at are crashes and outcomes of crashes. So what you see here are several corridors. So this is called Maryland Parkway. This is Sahara, and the next slide I'll show you more of Sahara, Charleston Avenue. So you see we have some north-south corridors, east-west corridors, and the colors of the dots. For each corridor we have the color of the dot represents a crash in that. And I'm not telling you on this slide whether that was a K, A, B, C, what the outcome was, but just to visualize how many crashes are there. Then here were two buffers that we looked at, the extent, so Sahara Avenue from here to here, and they said no, extend Sahara Avenue further. So just by using tools that we have in GIS, we use ArcGIS Pro, you are able to buffer and then come up with how many crashes are within this buffer zone. Then we further dissect it into K, A, B, C, O. The next thing we are looking at is, okay, how many of these crashes involve pedestrians or bicyclists? If we were to improve the infrastructure for pedestrians and bicyclists, we likely will reduce those outcomes. So then we can go to the crash modification factors or crash reduction factors, what we talked about yesterday, day before yesterday, to say, okay, if we made this improvement, maybe we will reduce it by 8%. So if we had 10 crashes over the last 5 years, we will reduce it by 1 crash maybe. And how did we summarize the data? There are 2 ways I wanted to show you. On this, on the x-axis are the corridors that we are evaluating, the one that I showed you on the first map, several north-south, some east-west. And for each corridor, just please follow me on the screen. I'm going to pick this one, Maryland Parkway. That is the street, the major street just on one side of the university. And it's a very heavily used public transit route, one of the most busy outside of the resort corridor. It carries the highest, one of the highest passenger ridership. And one side is university, the other side you have eating restaurants, small, a lot of things that will attract foot traffic between the university and across that. But as it is presently built and operated, it has 3 lanes of traffic in each direction. Very little for pedestrian accommodation. So that is being totally redone. So here, the bottom blue are pedestrian K-type crashes, fatalities. The next red is A-type, how many pedestrians were injured, serious injuries, A-type. The next green is non-motorist, non-pedestrian. So this could be bicyclist, two-wheeler, wheelchair-bound person. So the number of people killed, and 5, the purple is those who suffered serious injuries. And the top 2 bars, the lighter blue, is for motor vehicle occupants who are killed, and the orange is motor vehicle occupants who sustained A-type injuries. So here is a count. So when I look at it across the board, very quickly, just in 5 years, 2019 to 2023, you are looking at 90 plus crashes on this short segment of the about 4 kilometers, 4.5 kilometers, less than 3 miles. We had, if you look at total, over 90 crashes of K or A type. And if I look at pedestrians, I have 15 pedestrians who were killed. So same way you can look at it. So now by looking at it very quickly, you can see which corridor had a higher number of pedestrian fatalities, total injuries, and our interest is mostly the K and A type to pedestrians and non-motorized users. So the top two parts of this bar is not particularly relevant when you are trying to identify what are the needs for the non-motorized users. Another way to present this, as I have told you, is to look at it as proportion. So each bar is 100% here, but what percent of those are the K plus A for pedestrians, bicyclists here. So if you look at it, just ignore the top blue and orange. So you can see that it varies from about 60%, 65% here to the low of about 50%. So if we can, now the question is, they don't have money to build all of this, so they need to prioritize. The trade-off will be, do you take the count of crashes, now a frequency, total number of crashes, or do you take the percentage, or how do you weight the two together? So this is a very simple practical application of the data. Any questions, observations for people online?
No, we understood that mobile data was also helpful in generating these figures. Which data are we talking about?
They have the location, speed, acceleration, time, everything. So it's not that it's your mobile phone or his mobile phone or her mobile phone. They have hundreds of mobile phones that are going through that, and they are able to discern who is going straight, who is going left, who is going through.
So in a way they are able to scan the devices.
Yeah, I don't know enough about the technology. It's their patented technology. I'm excited that I'm getting data that I can use. From what they tell me, it is primarily based upon mobile phone. But I'll show you some other examples where we have sensors all around the intersection and cameras. So the previous set of videos I showed you, Dirk, they use the camera feeds, and then they use computer vision tools and techniques to figure out, is that a person walking, wheelchair, bicycle, so on and so forth. They can even tell whether it is an adult or a child, and they can extract the data for you for a price. They are in the business to make money. All right. So here is another example of an ongoing project that I have with two collaborators. Brendan Morris is an electrical engineer and computer engineer. He specializes in computer vision and so on. So some of the work that I showed you earlier also is based on collaboration with Professor Morris. Paul O, he's a professor in mechanical engineering who does a lot of work with robotics, okay, and drones. So, and Bayu Lin is a computer science faculty member. So you can see how the team has people from multiple disciplines who can bring their experience, their expertise to bring up. So what we've got is, we are fortunate that we have funding from an agency called the National Science Foundation. It's a very prestigious funding agency, very challenging to get funding from them. And so what we have is, we are developing a real world lab. I showed you a map of where Las Vegas is with respect to the airport. I showed you Maryland Parkway. So we are instrumenting intersections in the near vicinity of the university on roads that bound the university and a few that are close by. And the goal is, we don't know when, but to try to facilitate transition to a completely autonomous driving environment. So how do we use sensor systems to do that? And we're also trying to capture and emulate or identify road user behavior. Not as much the drivers in vehicles, but are people outside the vehicles. That's a bigger concern for us. Can you detect them? Can you see when they are intending to cross, they start, stop, so on and so forth, and can you make some decisions on that? And we are trying to do this in near real time. So there are several intersections, and what we are doing, V2X, is vehicle to X. It could be infrastructure, it could be vehicles, and here are the names of the devices that we are using, and the next slide has a little more detail. Okay, it doesn't show up well here, but I'm glad it shows up here. So with funds from the grant, another grant, Professor Morris bought a car in 2019, and modified it, instrumented it, will show you with a whole bunch of sensors. So here's that vehicle. If you look carefully, there are sensors, radar, LiDAR type things mounted on top. And here's what the instrumentation is in the back of the car, where we otherwise might have put luggage. There's a whole bunch of instrumentation there. And here are some of the details of the instrumentation. So where do we use this? We get a whole bunch of driver and road user behavior data to try to figure out how might we identify problems and avoid problems. So that's the whole goal. So here's yet another project where we are getting data from Dirk. As I mentioned in the previous thing, this is where the university is located. So here are 3 signalized intersections in the vicinity of the university, for which I'm going to show you data in the next few slides. So here are the cameras mounted at each of these locations, and I'll show you in the next slide. We have visibility during daytime, visibility during nighttime, because we want to make sure that our solutions will work. So on the left side is a set of photographs, 4 approaches, 4 sets of cameras, daytime. On the right side is nighttime. But it's not just the capability of the cameras. In the Las Vegas area where we are fortunate that we have fairly good street lighting, so that helps illuminate the roadway too. But the point I'm making is technology is there today. Even if it is nighttime, you can discern it. If there's lighting, it's even better. If there's not good lighting, you may have to go to more expensive types of cameras, night vision cameras. So some of the next slides are very busy, lots of detail, the fonts are small. I will try to walk you through it. These are just screen capture shots. And I once again want to acknowledge Brendan Morris, Professor Morris from electrical engineering, and my colleague Erin Breen. Her background is not engineering at all. All her efforts are community and stakeholder engagement. She looks at work that we do, the data analysis, so on, whether she works with elected officials to come up with policies and regulations, or whether she works with the police, or whether she works with the neighborhood homeowners association or schools. That's her work. She lives and breathes to do that. Once again, the point I'm making is these are collaborative efforts that take different people. We can come up with the best solutions, but if we cannot get people to accept it, it's challenging. Let me digress before I go. So many of the things that we see in transportation, I would say in other areas, but I'll focus on transportation, whether it is, and safety. Overcoming these challenges is steep. It's a steep challenge, right? Would anybody disagree with that? You may want to write this down. What do the letters STEEP stand for? STEEP. We know that as a word, steep is very difficult to climb, steep hill. Pardon? Please speak up.
So it is a type of terrain.
It is a type of?
Terrain. TERRAIN.
Terrain, yeah, type of terrain, steep terrain. I'm going to use that word, and I hope you will keep this with you and use it in your careers. Whatever solution you come up with needs to meet these 5 letters for it to see the day of light and have an impact. S is for socially acceptable. Society should accept the solution. T is technically feasible. Most of us come up with solutions that are technology based. Technically, yes, it can be done. E is for environment and energy. From those perspectives, it should be doable. The second E is for economic, money. All of these things cost not small money, big amounts of money. If you have all these 4, you've met most of the things, but the last one is P, politically saleable. If the elected officials will not own it, if they will not accept it as and make it their idea, if you don't have this steep, most of the things that we come up with if you're missing one of these, will not see fruition. So sorry for the digression, I've been meaning to share this with you, is think about when you come up with solutions, think about these aspects, just not, okay, I did my MATLAB calculations, or I did my highway capacity manual calculations, or speed, oh, this is the radius of the curve, so on and so forth. That's only one part of the whole process. I see you looking at me with surprise. No comments? All right, so now let me walk you through these next set of slides. I have 10 more slides, and I will try to stop in another 15 to 20 minutes or so. So here, this is University Center Drive and Harmon Avenue, which is one of the intersections adjacent to the university. Here, this is, the cameras are continuously recording, and then they have enough using AI techniques. When there is an issue, those frames or those sets of frames are separated, and Dirk is the company that does this. They then come up with these red bounding boxes to help us from the transportation side. So what you have here is the location is University Center at Harmon. The date is 2/22/2025. I told you in the US we put the month first, so that is February 22. The time is 1:13 and 51 p.m. So kind of midday. What do we have here? It's a near miss. The speed of the vehicle was 14 miles an hour. And what was the type of near miss? The vehicle cut off who was the other one. You can see, I'll get to that. And what was the detection area? That is the west leg of the intersection. Did you have a question? No. I saw your hand go up. That's I'll do that too.
So I have one question.
Yes.
Here.
Yes.
So when we are talking about near miss, can you talk in terms of values also, like kinematic values? When we are saying near miss, like we are seeing the video of the near misses.
Yeah.
So can you give a glimpse of
The answer is here. Bear with me.
Okay.
So here, the road user A is a bicyclist. So you can see the bicyclist here. And the bicyclist was traveling at 10 miles an hour and making a right turn. So going from here to there. And the direction of movement was westbound. Road user B is a passenger vehicle traveling at 14 miles an hour, going from here, making a left turn. So the point of conflict is this person making a right turn, the bicyclist making a right turn, and the motorist making a left turn. So the surrogate safety measures here is post encroachment time, which is not relevant here, time to collision, 0.4 seconds. Okay, so near miss. So we will have to define, in the Indian context it may be 0.001 second. People are so tolerant. In the US context, again, it may vary from one location to another. It is for us, we can code it in, saying that for me, if there's a potential conflict and time to conflict is less than 0.7 seconds, characterize it as a near miss. In other situations where you have maybe a lot of elderly population, we have in the Las Vegas area and many parts of age restricted communities, where a community neighborhood, a housing colony has people living over a certain age, 55 years of age or 60 years of age. Their mobility is much smaller. Their walking speeds are maybe 2.5 feet per second as opposed to 3.5 feet per second that we use. So for them, the time to collision may be 1.5 seconds, not half a second. They are not able to jump off and get away. So it is up to us to decide what might be an appropriate metric where we have a near miss. Other things could be physical separation. Here we are doing it in time. But in India, maybe it is the space. I told you, I get so nervous going in a car. If I put my finger out, maybe the car next to me will chop it off. People are tolerant to that. Maybe I'm exaggerating. But vehicles come within maybe less than 0.35 meters, 1 foot or so. If that is tolerable here, that's not a near miss. So then you will put the threshold in terms of spaces of if it is less than 0.34 meters. Did that answer your question, Ritesh? All right, so then so this is how we look at it. I'll go to the next. This is actual crash that happened, and so it captures the frames before and after. Once again what we have here, the location. So each event has a complex ID number. So once again we can link this to, there are other data feeds that are coming. At the same time we can go and look at this instant what was the traffic signal timing, what are the signal head detection indicators on all legs, on all approaches. So that unique identifier event ID is important there. The detection was, this was about 3 months ago, December 2nd 2024, 9:23:13 a.m. The detection was on the east leg. Road user A was a passenger vehicle traveling at 19 miles an hour, making a left turn going from south to east. So going southbound, making a left turn to go east. Okay. Yes, going south, making a left turn to go east. For us, left turn is the same as right turn here. And the second user was a pedestrian walking at, or set of pedestrians walking at 4 miles an hour, and they were just doing a through movement in a marked crosswalk. So, and you can see they will give you the video feed of about 15 seconds, that's reasonable enough time. The previous one too, it may vary from a few seconds to maybe 30-35 seconds. And on the previous set of videos that I shared with you online, you saw most of them were between 15 seconds and 45 seconds or so. So those are all video data, we can visualize it. But if we want to automate the analysis, we have to get it in some numerical format. So here are examples that translated each such event into some numerical values, and I'll walk you through this. This is a busy slide. The next slide I will zoom in. Okay. But what I wanted to show you here, this is the company Dirk, and they are a Dubai based company who have a lot of operations in North America and across the world. So you can look at determine what you want: location overview, safety insight, what type of events do you want, statistics about the events near, and you can select what you want. And here traffic insight, so here is safety, traffic. Do you want vehicle counts? Do you want vehicle classification? Car, truck, bus, so on, or even within passenger vehicles, different types of vehicles. Peak hour analysis, turning movement counts, vulnerable road user counts, speed distribution, and so on. So there are lots of options that they have pre-programmed, but if you or your organization want something different, if it is feasible, for a cost, most of these companies will retool the interface to allow you to get this. So then what do we have here? You have a search capability and what you display. So the first column is the event ID. What I showed you on the previous slides in the videos, you had an event ID at the top. So the event type, and in this case it is a near miss with a vulnerable road user. So all of this is near misses. Detection area, east leg, south leg, north leg, so on and so forth. Date and time. The next one is speed. What was the type of near miss? It's just not categorizing it as a near miss. The motorist cut off the vulnerable road user. Right of way, that is, the pedestrian had the right of way to go in the crosswalk, but the motorist did not yield the right of way. Here's one more term, Ritesh, you were asking. This is post encroachment time in terms of the collision paths of the vehicles. How many seconds after, or vehicles or the users, how many seconds after one user crossed a point did the other vehicle come? And in the Indian context, it may be as less as 1 second or 2 seconds. In the US context, we are concerned about 3-4 seconds also. Time to collision, what I talked to you about. Gap times between when events happen. And severity, all of these were characterized as low. And who was the impacted road users? The passenger vehicle and pedestrian, passenger vehicle, pedestrian, and direction of the vehicle travel. Let me go to a zoomed in version. The same thing. Now this is from more recent, February 27th and 28th. So you're looking at less than a month ago. So we are able to do these analysis in near real time. We get these data feeds. We have a connection thanks to our partnership with the city, the municipality, several other agencies. So we could probably do the analysis of something that happened at 9 a.m. right now within the hour. But there are some QA/QC delays depending upon if you own the access to the data, you may be able to do it near real time. For us, we have to, there's a little bit of a delay that they may want to review certain things. Once again, you have the event ID, event type, non-motorist vulnerable road user, detection area, which segment, date, time, speed, and type, so on. And here, this one, Dr. Morris just filtered the high, and you can look at the time gaps and time to collision are less than a second. So these are the tabular data. We can then look at this hundreds and hundreds of these either at one location, in one area, along one roadway corridor to figure out the extent of the problem. Remember, I started by saying that crashes are fortunately rare events, but for every crash, we have thousands of near crashes. So how can we learn from these? So once again, this is a busy chart, and what I have in here, I will show on the next chart. What you have on the left are filters or analytical or queries that you can set or customize within certain ranges that they provide. Okay? And then here's a dashboard that gives us an overview, and you can pick it. I'll show you how you can pick it. In this case, so this was Monday, March 3rd, so this month. Top 3 near miss situations. This was a bicycle and passenger vehicle through movement. Bicycle, passenger vehicle, bicycle, passenger vehicle. What was the type? It was cut off weekday. This happened afternoon 12 to 4, 12 to 4, morning 7 to 9. How many? 433. So that's. Now let me just go to the next slide where it is a little clearer. This is for 1 week, if I remember, February 25th to March 3rd, or February 26th to March 2nd, something thereabouts. Once again, within the past month. Here is an overview. Now if you're trying to present this to a manager or somebody higher up, they don't want to get into all those details that we showed on the tables. Here's an overview. Here are the near misses with high severity, low severity. You had 4 near misses with high severity. We had 18 in low severity. By time of the day, when did it happen? Monday, Tuesday, Wednesday, so on. By time of the day, here's the day of the week, time of the day. And what were the type of movements? Left turn, through, right. And near miss by direction, going northbound, northbound to eastbound, southbound, southbound to westbound, so on and so forth. You can, and what is the type of near miss? Either did not yield the right of way or cut off the other person. So these are the dashboard gross metrics, and this is what you can use to determine what might be an appropriate countermeasure or set of countermeasures that would help remedy the problem that we have at hand. Questions, comments, concerns? Okay, I see several people joined online and in class after I had made an announcement early on. Okay. Ritvik, I'm going to charge you to repeat the announcement that I had, the problem that we are going to work on in the tutorial. If you will help me, help the others understand the challenge I gave you, please use the microphone. Please pay attention, those of you who are not here early on. I will call on every one of you in the tutorial session for this.
So we have a tutorial. So first task is to identify a place on planet where you have spent maximum time, and it should be after your 5th year, 6 years onwards.
First standard onwards.
Yes, yeah. First standard onwards. So if that is done, then we move to task number 2. You have to figure out what are the 3 most critical road safety challenges that you see in these last years. 3 most critical road safety challenges. Hope that is clear.
Thank you. Did everybody online hear the questions? Is there anybody who did not hear the question? Thank you, microphone. If you did not hear the question, raise your hand. Otherwise, you're going to be held accountable for the question. Those in the classroom, Shashi and group who are sitting in the last rows, why did you choose to sit there? There's so much space here. I know you didn't want to disrupt the class. Thank you. Right.
So first question is not clear.
First question
Hello.
is, where on planet Earth have you spent the most amount of time after you were 5 years of age, or that is after you would have started studying in first standard? Which city, town, village, district, you choose where what the geography is, because under 5 years of age most of us don't remember a whole lot about this. After that we would likely remember. Was that Chandrika Verma who asked that?
Yes, sir, I have heard the question.
Okay, thank you. I couldn't figure. Thank you, Ritvik, for helping me. So, Shashi and group, you need to relay the question to your newest teammate. So, let's move to one more thing where I am interested also in pedestrian exposure. So far we were talking about all vehicular movements, and on this slide it is very similar to what we saw earlier, but I will walk you through the steps. Here this is the safety score we can choose: last 365 days, last 90 days, last 30 days. So this metric is for the last between February 4 and March 3rd of 2025. And on the y-axis is the count, and here are various indicators that we have. Safety score, it's not a count, for this week, week 1, week 2, week 3, week 4. The next I want to go to are safety insight snapshots. Within the last 7 days, what are different types of events? And you have a score also, 79, the number is there at the bottom. I apologize for it not being very visible. Here you had 0 events of this type, 50 events, which represents a 79% reduction from the previous comparative time period. So remember what I talked to you about earlier. We are interested not only the absolute state or absolute count, we are also interested in the change of state. What has been the change for good or for bad? So here we have 79% reduction on conflicts with pedestrians. Right turn conflicts, 69% reduction, and so on and so forth. You get it as a snapshot. Then looking at it further, we are able to extract, here are the vehicle movements on each approach. How many going straight, how many turning right, how many turning left. But if we are looking at pedestrians, we need to get pedestrian counts too. So from this DIRC interface, we are also able to get the pedestrian movements for the same period of time. And none of this is done manually. It is taking advantage of whether it is computer vision, pattern recognition, image recognition, and other machine learning tools. You train the system to say, okay, this is a pedestrian, this is a bicyclist, so on and so forth. I do not have expertise in that, but I work with people who are experts in that, so that we can collaborate to address broader societal needs. And based on an analysis of all of this, we come up with a heat map or so, saying where do you have the highest concentration, highest intensity, highest challenge, highest need of the problems. This is a different location, but you get the sense. Similarly, you can see here we had increases. Last one I showed we had decreases. Here we have some increases. So this is Flamingo Road at University Drive. This was Flamingo Road at Cambridge, close to the university. And this is a zoom in of one of the previous ones, like how we extract intelligence from data. Now we have something actionable. We can show this to various people, not just the engineers or the planners. We can take this to the neighborhood homeowners association meeting, the school teachers, parent teachers meeting. Here are actual problems. Here's what we are trying to do to help improve the situation. We need your cooperation, we need your buy-in, we need your participation. So as I mentioned, it's just not doing the analysis, but communicating what you did, what it means, and how would it affect them. And pictures, graphical communication tools are absolutely important in this. So I said 10:30 and I am right there, and I can start the next exercise if Chai is not going to be here till 10:45. Chai is there? Oh, thank you so much. So once again, please buckle up, everyone, every position in the vehicle, every time. Before you start, the other person starts the engine or you start the engine, and until you turn off the engine. I see some people doing this. Yes, do it, do it, do it. Okay. Lead by example. I'm not afraid to shame other people in the vehicle if they disobey such simple things that can make a life of a difference. All it takes is a fraction of a second of no fault of our own. It may be somebody else who violated traffic laws, came and hit our vehicle. And I have some very personal thing why it is. I lost my father-in-law when he was 45 years of age. He was a professor of chemistry. He was a dean of a university here in Cochin. You know how? He was in a motor vehicle that had 8 other occupants going to the Puri Jagannath temple. Everything. The driver kind of nodded off, fatigue, just dozed off for a moment. The vehicle rolled over. It was on an embankment. Nobody was wearing a seat belt. Everybody was ejected. The vehicle landed on my father-in-law. His ribs broke. He was the only one who had any injury. He died 40 minutes later. Safety is personal. So if this doesn't send you a message of the importance of wearing seat belts, I hope you never ever come across such a situation in your own family, circle of friends, but keep this in mind. Seat belts save lives.